Edgardo Saucedo from the Catalonia Institute for Energy Research in Barcelona, and I will present you some status about Kesterite technology, because in my life we mainly work with this emerging photovoltaic technology. This is the outline of my talk. I will start with a short introduction, explaining you a bit the interest on these Kesterite materials, and then I will move forward to discuss two issues that in my opinion are very relevant for Kesterite. Is the status of doping and alloying on this material, presenting some interesting examples and the impact and what we know until now about these two issues. So this is the very famous efficiency Gantt chart of Unreal, with most relevant technologies are including. And in terms of this, in thin film technologies, we have two beautiful materials, copper indium gallium diselenide and Catalonia, with efficiencies really comparable to those reported for crystalline silicon, with production cost also extremely competitive. Then, if we have these two technologies, why we need to explore new thin film photovoltaic material? This is mainly because nothing is perfect, of course, in the world, and even if we have these two beautiful materials, both of them contain critical elements. Indium, gallium, and tellurium are very scarce materials in the Earth crust. This means that production at terawatt levels is very difficult, if not almost impossible, with this technology. So if we would like that photovoltaic technology becomes really a spread technology over the world, we need to develop materials that are from the very beginning abundant and sustainable. And in that sense, and after some time of research in this new material, this is just a table with some of the most relevant ones that are being studied. Kesterites become the most relevant one in terms of efficiency and performance and sustainability. So this family of material formed by copper, zinc, tin, sulfur, and selenium, becomes really very relevant and are at the forefront of these emerging pure inorganic thin film technologies. Susan has explained almost everything about Kesterite structure and why these materials are very interesting for photovoltaic application. So I cannot add anything else what she already explained, but basically one of the main advantage of these technologies is, of course, that the structure is very related to copper indium gallium diselenide and Catalonia, so we expect very similar optical and electrical materials, and we can use all that we previously learned about these technologies. And in Kesterite, as Susan presented very well, so we have planes with copper, tin, copper, zinc atoms, and the list of the main advantages is that Kesterite is mainly formed by low toxicity and abundant elements, normally exhibit p-type conductivity, has direct band gap, so we need very thin layers for absorbing all the sunlight, and we can play with the composition and tune the band gap. This is very relevant to adapt the band gap of our material for different applications and advanced concepts, and of course is highly compatible with SAGES. This means that a company producing SAGES can easily shift to Kesterite. But this is most probably the most complex family of materials studied so far, fully inorganic, for thin film photovoltaic application. So of course we have a lot of challenges to solve. Among them, and Susan already summarized extremely well almost all of them, is that copper and zinc are isoelectronic elements, so they easily exchange in the lattice, forming this kind of defects and disorder like copper and zinc on copper and so on. And tin is a very problematic element because it has different characteristics that make tin a complex element to work with. In particular, tin forms volatile species with selenium and sulfur, so it's really very complicated to control it in our material. It's a multivalent element, so we always have the risk to form reduced tin species that can be really problematic because introduce deep defects, and tin strongly interacts with other elements like alkaline elements that are very relevant for chalcogenide. So the control of tin really is one of the big issues also in this technology. And in terms of zinc, it's the less problematic one probably, but also can be volatile, the metallic tin. So all the technologies that use tin metallic during the preparation of kesterite have to consider this as well. In the status of kesterite solar cell, if we compare the history of this material with SAGES, we can see that this is like a teenager technology with 20 years old, more or less. The first working device was published in 1996. And if we consider this like this 0 year, this is the evolution of the efficiency of kesterite, and this is the evolution of the efficiency of SAGES. SAGES is more or less 40 years old material. And then more or less both of them follow the same trend with a very similar slope, even a bit higher for kesterite, but of course we are still far from this technology. And we need to understand why in order to make possible this progress in the next years. And of course, if we compare these two materials, we can have some ideas how to solve the problems that kesterites are facing. This is a comparison of the maximum efficiency reported so far as a function of the bandgap for kesterite and for SAGES. And what we can notice that for these relatively low bandgap materials or wide bandgap materials, the efficiency difference is not so high actually. The kesterite with bandgap 1 electron volt is about 12% more or less, and chalcopyrite 14%. And for the sulfur compound, for wider bandgap compound, even the difference is less important. Kesterite is about 11%, and C is about, say, 11–12%. The huge difference is here for this intermediate bandgap. And for really jumping from this level of efficiency to this level of efficiency, SAGES has introduced three different, or we can say two different strategies. Sorry. Mainly alkaline doping and also gallium doping, gallium alloying, sorry. This means that SAGES for pushing the efficiency from around 12–14% up to 20%, introduce these two type of strategies, doping and alloying. So this highlight the importance to study this type of processes on kesterite. Then if we consider the structure of kesterite that is formed by copper, zinc and tin, then we can have an idea what kind of alloying and doping is required for these materials. And in principle, with doping, of course, we can have intrinsic doping, so we have to play with the same structure, modifying copper, zinc and tin and see what happens, and if we can win something. We can have extrinsic doping, and learning from SAGES, of course, alkaline doping can be relevant, but also it will be very important to study isoelectronic doping, like with silver, cadmium, germanium, silicon, or even with other materials like indium, plumb, bismuth, and antimony. And for alloying, Of course, cationic alloying can be very relevant as well, and the most important one probably is the substitution of copper by silver, zinc by cadmium, and tin by germanium. Then starting with doping of kesterite, so this was already presented by Susan, and the main thing is that we don't have just one kesterite. We have at least 12 different types of kesterite. And this is just changing the kind of intrinsic doping, the composition of kesterite. And each of these kesterite have particular different point defects, and several of them are really detrimental. So first of all, to understand this is extremely relevant. All the work presented for Susan is really the most important starting point, because we will understand at which kind of intrinsic doping we have to work, and then try to improve this intrinsic doping. And for studying this, in my group, time ago, we started to perform an experiment with what we call mega sample. It's just one sample, you can see here, 5 by 5 square centimeter, where all the interesting compositions are inside. So it's a graded compositional material. Then in just one sample, you can study all the compositions together. In this kind of samples, we can prepare more than 200 different solar cells, each of them with different composition. And of course, this experiment covers the full compositional range of interest. So we have access to all this type of kesterite together. What we can start to observe is that if we plot the efficiency, the VOC, the GAC as a function of the different type of kesterite that Susan has very well presented, we obtain maximum efficiency and VOC and GAC at different regions. So I was speaking about intrinsic doping. So what we found is that most of the working devices actually fall into the region that Susan predict as the most interesting one, and where kesterite shows only shallow defects in principle. And this is observed here. It's between the A, B, and E type lines, where you obtain the maximum efficiency, the maximum VOC, the maximum current of the devices. This gives us the input that we have to work. Actually, this is the experimental demonstration that this is the most relevant composition. And this, of course, is in agreement with other theoretical work that demonstrate that all the defects that we expect in these compositional lines are mainly shallow defects, and that we minimize the probability of formation of the defects that normally are very detrimental. But we have worked a lot with that in several groups, and we think that in terms of intrinsic doping and control of composition of kesterite, we know a lot. And that modifying only this intrinsic doping is almost impossible to increase further our efficiency. What? I don't know. This is probably because the source. Then in this, I hope that this is not the case. Wow. This was not like this previously. This will be almost impossible to follow. Let me check if... Keynotes. Here. Let's see if here is the same. It's the same. I don't know.
You lost your fonts.
Yeah. No. Now I recover it. Okay. Fast edition of the presentation. I'm so sorry. Then in terms due to that with intrinsic doping, we almost have done a lot of work, and we know that further big progresses are not expected with that. We start to study alkaline doping. Alkaline doping is very relevant for CJS, so we expect the same for kesterite. And in that sense, we can consider that it's really a hot topic on kesterite, and you have many different ways to introduce kesterite that are summarized here. I will not go deeply, but it's relatively easy to introduce alkalines on kesterite. I put select all. I switch. My gosh. I'm very sorry, but in the revision of this, there was not a problem with the sources. I don't know if I can define. No. Well, it's really. I will try to do like this, please. You have to trust me what is writing here. I think the most important are the fibers. So in terms of alkaline doping, there is first a controversy in the literature. What is the best alkaline? Some works predict sodium, other potassiums, other lithium, and so on. And during some time, people were confused about this until the works of our colleagues from EMPA that they show that actually in kesterite there is a peculiarity, and this alkaline element interacts a lot with tin. Then each alkaline element requires a different tin quantity. So also depends on your on the composition of your kesterite, the optimal quantity of lithium, sodium, and doping, explaining why different groups are obtaining different results. For example, if you are working with potassium, you need less or more tin than if you are working with lithium, or less tin than if you are working with lithium. Also, our group demonstrates a strong interaction with this tin element. Actually, we are working with germanium, and what we observe is when we increase the germanium quantity, that is very similar to tin, and replace tin in the lattice, sodium oxides start to appear. So there is a strong interaction between the quantity of tin and the sodium quantity that you can incorporate in your kesterite. And this is something that we are trying really to understand. And even just playing with this, you can change a lot the carrier concentration of your absorber. So in terms of alkaline elements, now we know that it's very relevant that lithium, sodium, and potassium probably are the most interesting one, and that we have to take care about the tin concentration we put in our absorber. Then we start to study extrinsic doping with other elements different than alkaline elements. We test several of them, and with what we find that germanium is the most important one, or the most relevant one. Why? Because we observed 2 or 3 years ago that including very tiny quantity of germanium, we obtained a very huge increase in our efficiencies. And germanium is replacing tin, so in somehow we have an idea that touching tin also we can get really huge improvement. And in particular, we observe a very large VOC increment, and this is one of the main problems of kesterite. So germanium can be useful for improving the VOC deficit of kesterite. Among the positive effects of germanium, what we observe is that we obtain really very big crystals using germanium, and at that time we proposed this model that germanium is forming some liquid phase for improving crystallization. This was just a theory, and very recently we succeeded to prove it experimentally, and we are writing now the paper to show that germanium also can act as a crystallization flux for kesterites. At that time, collaborating with IMRA in France, we obtained almost 11% efficiency, and that can be very reproducible. Once we start to introduce germanium in our system, reproducibility becomes much higher. Then we need to understand what happened with germanium, what is the other effect, because this we cannot only explain with these huge grains this efficiency improvement, and what we do is a break-off experiment. This is a typical thermal routine in our lab. We start with copper, zinc, tin and germanium metallic layers, then we anneal in this two-step process. In the first step, at relatively low temperature, 400 degrees, we introduce the chalcogen, we form the precursors, and we synthesize the kesterite. Then we increase the temperature up to 550, 570 degrees to crystallize them. So stopping the reaction at different points, we can learn about what happened during the synthesis of kesterite. And stopping here in the first point where kesterite is starting to be formed, when we don't use germanium, basically what we observe is that we have a strong separation from copper phases and the other phases. We don't have a very good mixture between copper, zinc and tin. And we have a lot of tin loss. Basically, in this process, when we don't include germanium, a lot of tin is lost in the atmosphere. Then combining X-ray diffraction with a Raman spectroscopy, I will not show here because it's quite complex work. What we conclude is that in that case, the kesterite is formed via the reaction of the big binary compounds. Copper selenium, zinc selenium, tin selenium binary compounds react to form the kesterite. And then when we finish all our crystallization process, we obtain quite good layers, but that can be improved. Nevertheless, when we include germanium, we observe a very different picture. We have a very good copper and tin mix, and also we don't observe tin loss during our reaction. This means that in somehow germanium prevents the tin loss. And analyzing all this process with Raman spectroscopy and X-ray diffraction, what we observe is that the reaction mechanism changed drastically. And we are only forming copper, tin, selenium ternary compound that react with zinc selenide forming kesterite. This is an advantage because we are not forming any volatile species here. We reduce the tin loss and all the problems associated to this. And also it's a simpler reaction mechanism. You need only 2 molecules to form kesterite, so the probability that the reaction is completed during your synthesis process is much higher. And this is a clear advantage. And in that case, what we observe is that you can obtain even this kind of grain structure, these beautiful, very big grains. And playing a bit with germanium, we succeed to obtain this 11.8% efficiency pure selenide compound with some tiny quantities of germanium, collaborating with AST in Japan. So this efficiency was measured in both places, in IREC and in IST, in order to confirm that this is a real value that we are getting. And we publish, and you can have all the details about this work in this paper in Energy and Environmental Science. Let's move to alloying. Then first, as Susan presents, silver can be very interesting for replacing copper, and also germanium, of course, replacing tin. Then, going fast about silver, it was really ABM presenting very nice results about the silver alloying compound, and what they found is that reasonable good efficiencies can be obtained with silver. But the problem is that when you start to introduce silver, you not only change the structure, you change also the conductivity type. And the silver compound is N-type compound. Then it was demonstrated that with silver you can play with the band gap, obtaining quite nice efficiencies, but the problem is that we have to change drastically our solar cell device structure, because now we have an N-type absorber and not a P-type anymore. So this means that we have to really rethink our devices, and this is, for the moment, can be a bit problematic in terms of the introduction of silver. Nevertheless, with germanium, there are several works using germanium for alloying kesterite, and all of them has demonstrated a very positive effect. Germanium is easier to work than tin, so you can easily tune the backup using germanium. You can get very nice transport charge properties and very good efficiencies as well with germanium easily, or quite easily. And more recently, my group collaborating with Helmholtz-Zentrum Berlin, with Susan's group, we demonstrate also that germanium not only can change, you can use for changing your backup, but also accumulate at the back, like gallium in copper indium gallium diselenide. So we can use germanium for advanced graded bandgap concept, like the ones using for copper indium gallium diselenide. So germanium can be the gallium for kesterite. And this can be very relevant in the future for implementing graded bandgap concepts in this technology. And summarizing what we know about alloying, you can see here some of the best results reported using silver, cadmium and germanium, and it's clear that germanium gives really very high efficiencies, so comparable to the tin pure compound. So this is, in my opinion, the most reliable result and most reliable element to use in the future for a graded bandgap concept. So this is, I will skip this and go directly to the conclusions. So what we learn about right now about doping and alloying kesterite in terms of doping, intrinsic doping is very relevant, but right now I think that we have a lot of background and knowledge, and we know where we have to work and what kind of composition. Alkaline doping is also a very relevant issue. Lithium and sodium seems to be the most important one, helps to boost your efficiency, but it's not still the final solution to jump the efficiency up to 15–20% level. In that sense, extrinsic doping has shown very relevant effect on kesterite and mainly alloying with this kind of silver and germanium compound can be very important in the future to really boost the efficiency of kesterite, and we are working a lot on that because we believe that this is the way to demonstrate efficiencies higher than 15% for this technology. And in that sense, I'm just also very connected with all this session that deal with new or emerging thin film photovoltaic materials. We are launching together with IOP, the Institute of Physics in United Kingdom, a very nice initiative, I guess. That is because emerging photovoltaic materials become very relevant and inspired in the yearly published photovoltaic efficiency tables for Martin Grimm's in Progress in Photovoltaics. We will do the same, but for emerging material, thin film inorganic material exclusively. So very soon, in 2–3 months, we will have this paper yearly that Theo is also involved in this initiative, where all the years we will publish all the emerging thin film photovoltaic materials efficiency tables in order to inspire the research of all of you and all the people that is working in this fascinating field. And this also will encourage that you start to certificate your solar cell devices in order to be included in this table. I think that is very relevant for all of us that we are working in these new materials. And finally, I would like to thank the financial from Europe in the Infinite Cell project that we are collaborating with Susan, with Morocco and so on, the Star Cell project as well. And of course, Susan, for this very nice invitation. I'm very sorry for all the issues with the presentation. I'm so sorry. And thank you very much for your attention.